thanks everyone who is here today. So my name is Félix Chalumeau, and today with Ilan Coulon, we'll be presenting the work that we did last summer under supervision of Quentin, Cappart and Rousseau at Polytechnique Montréal. It was about having a constraint programming solver guided by reinforcement learning, and we are happy to release this work in an open source Julia package called SeaPearl.gl. So today we'll present you the background necessary to get on board. We'll explain how we did to have the learning embedded fully in the constraint programming solver. We'll present you our result and the analysis of those results, and we'll have a quick introduction to the future work we plan to do around this project. So this is all about constraint programming, so let's have a quick recap of it. So constraint programming problem consists of a variable that must take some values from limited domains and that must respect constraint. In the easier case, the fixed point algorithm will propagate the constraint enough to fix all the values from different variables and just find a solution. But often it won't be enough, so you'll have to use some variable selection heuristic and value selection heuristic to expand the search tree and eventually find a solution. And what we think is that we can have terrific improvements in performances while learning those heuristics. And we want to start with learning the value selection heuristic. So here is a quick overview of our architecture. So in green, you can see a classic CP solver architecture. And what we want to do is use a reinforcement learning agent to handle the value selection part. So we'll have time to see this architecture later. Let's now focus on the reinforcement learning framework and how it works. Reinforcement learning is all about having an agent acting in an environment and basically learning a policy to get as many rewards as possible in this environment. So what you need to do reinforcement learning in an environment is having a state representation of your agent. So in our case, it would be a state representation of the solving process. Then you will have to design a policy that will be able to map any state to an action. In our case, an action would basically be the value that we want to branch on. And finally, it's important to have some reward retrieved from the environment, so associated to each state action couple, to know, to have some feedback about if was your decision good or not. Some little overview of the related work that motivated our own project. So a few years ago, Bedon et al. Proved that it was possible to use reinforcement learning to learn basically a heuristic to find approximated solutions to problems, for instance, the traveling salesman problem. On the other end, it was shown that a kind of learning can happen in a CP solver, even without reinforcement learning. And more recently, Quentin and Cappart proved that it was useful to use a heuristic learn with reinforcement learning outside the CP solver and then use it inside the CP solver to do the branching. So what we want to do is go even further and have this heuristic learn directly inside the CP solver as a value selection heuristic and then use it after all. So our main contributions are the following one. First, a theoretical framework as well as an architecture, which is able to solve any kind of CP problems. Then we claim to have the learning phase fully integrated inside the CP solver, which means that our reinforcement learning environment has the transition which are CP specific, like for instance, backtracking transitions. And finally, we are happy to provide to the research community a fully hybrid open source solver that can be used by any searcher as a sandbox to improve the performances in this field. So now let's focus on how we did the learning embedded fully in the constraint programming solver. This raises three issues, like first, how to design the state representation, like the state of your agent in the environment, how to design also the agent in itself, like the network, to get a branching decision from your state representation, and finally, how to design the reward to have useful feedbacks to learn something from all of this. So Let's start with a proposition, a unifying proposition for your state representation. This would be basically a three-parted graph with the variable, the value, and the constraint being nodes of this graph. And the edges would be, for instance, between a variable and a value if the value is in the domain of the variable. And two variables would be connected to a constraint if they are featured in this constraint. And you will add to each node a feature, which could be a simple feature like a one-hot encoding, or more advanced feature like metrics of the variable, the value of the constraint, for instance, the degree of your variable or the number of value in its domain, etc. You can also want to have a more specific and problem-specific design. Will it be a graph or any other representation? And the package that we released is flexible enough for anyone to try another representation than the one that we just presented. Once you have this representation, you want to know how to branch. So here you have the state representation, the graph representation that I just presented, and you chose a variable to branch on. And now you want to automatically decide the value that you want to give to this variable. So here you have the feature, which, as I said, can be a one-hot encoding or some metrics about the solving process or about the variable. And you are going to use some steps of a graph neural network to diffuse information in your state representation in order to learn, like to get a latent representation embedding of this variable feature. And then once you have this latent representation, you want to extract it, pass it to a dense neural network to compute some Q values. Q values being the expected reward sum that you think you can get from choosing each value. Then you will use a mask from the CP solver to avoid branching on values that are not in your domain anymore. And you will finally choose as a final value to branch on the argmax of this output vector.
So here we've talked about how to represent the state of the presentation of the solving process. But another information the agent must get is the reward, which lets the agent know which action will lead to good results. Therefore, the design of it is crucial if you want to hope to have a good value selection heuristic in the end. We've started by doing a very simple approach, which is to give -1 at each time step to the agent. In practice, the agent will want to end the episode as soon as possible. So in our case, the goal would be to reach optimality as soon as possible. So that's what we want. But we hope that in the future, it will be possible to use all the metrics available from the environment, because the environment is inside the CP solver, to really improve this reward design and maybe get a better training in the end. So to do all this, we chose to use a language called Julia. Its motto looks like Python, works like C, makes it the best candidate here. It's very simple to get on board with Julia, but it's still very fast and very clean. Both operations research and machine learning communities are very strong and very active in Julia, and yet the community is still very young, fairly young, and very open to new projects. So this made Julia the best candidate to build the whole architecture in one single language for SeaPearl. Here you can see on the right hand side in green the constraint programming part, but in orange on the left the reinforcement learning part. So on the right you can see that we have the fixed point algorithm that will prune the domains as you would see in a classical CP solver, but it was designed to be able to update at every step, update the state representation, the graph, for example, to be given to the agent that will be able to take action on the solving process during the solving. So it is trained during solvings, and this value section will prune the domains, and then we'll run the fixed point algorithm again, and then we'll update the state representations, and so on and so forth. So that's how we build this architecture. And with this very intuitive way of building it, we decided to do some experiments to try to prove that it can be used in practice, and that it should be, and it is a good sign that we have good signs that we think we should keep working on that. So the first experiment we've done was on the graph coloring problem. using on instances of 20 nodes or 30 nodes, randomly generated ones. Here you can see at the beginning of the training that the DQN agent is as good as a random heuristic, but in the end it becomes almost as good as the minimum value heuristic, which is the greedy heuristic that takes the minimum value of the domain, which is a pretty good thing because we've not encountered better heuristics on this kind of instances. So doing the benchmarking, taking only the number of nodes needed to reach optimality, we see that, yeah, indeed, the DQN agent is almost as good at the minimum value heuristic. But here, time is not taken into account because the forward pass of the DQN agent is very expensive in terms of time. If we were to do the benchmarking, taking the time into account, the minimum value heuristic would completely outperform the DQN agent. So we thought it would be a good idea to try this on another kind of problem. So we did it on the TSPTW, traveling salesman problem with time windows, using a ad hoc representation, which is a fully connected graph whose nodes are the cities and the edges represent the distances between the cities. So here we can see that, yeah, at the beginning of the training, on instances of 20 cities or 50 cities, the DQN agent is as good as a random heuristic, even better sometimes. But in the end, it completely outperforms the nearest neighbor heuristic. So this is a good sign, but again, now it is only in terms of number of nodes needed to reach optimality. So the idea here was to benchmarking using time. And we can see that we could say that the DQN agent here competes with the nearest neighbor heuristic. So sometimes it is better in time than the nearest neighbor heuristic, which is, I would say it is a good thing because in those very big instances, the forward pass of the neural networks are very expensive in terms of time. So we thought this would be a good sign for us to do some future work of other researchers to do it. We've identified some domains, some things that could be improved in this work, and some new ideas that could be tried to improve those results. So on top of improving the elements of the existing pipeline, because this solver is a very early version of it, we consider, for example, extending this to variable selection heuristics. We've only done value selection heuristics, so it would not be that hard to do it on the variable selection heuristic. Also, we think that when you're solving, finding good solutions or trying to prove optimality can be considered quite different. So the idea here would be to train two different reinforcement learning agents, one that could find good solutions and one that would prove optimality. And you would change strategy during the solving process, doing an arbitrary decisions. And last, we could also reduce the action space. Here, the size of the action space is currently the size of the maximum domain. This leads to very big action spaces. We could decide to reduce it to only a size of 2 by having the first action being taking the bottom half of the domain and the second action being taking the upper half of the domain. This would reduce the size of the domain and maybe ease the training in the end. So what we would like you to take home would be that we have built a full constraint programming solver here. It can train and use reinforcement learning agents as value selection heuristics. It comes as a whole open source Julia package that can be easily downloaded and installed. And every part of it is completely modular. And it was proven to do better, at least in terms of number of nodes, than man engineering heuristics on the TSPTW. So we think it's a good sign that because it's completely modular, other scientists and researchers could use it as a sandbox to try a whole lot of new experiments using the GitHub repository by contributing or giving new ideas on this very active repository. And a whole team in Montreal is still working on this package and has already started implementing some new ideas that we've had. So yeah, please feel free to come and contribute. And I would like to thank you for your attention.